Let's carry on with the next very interesting talk. Our next speaker and last for the day is Hao Shen from the University of Wisconsin-Madison. We'll be talking about SPDE limits on the six-vertex model.
Okay, okay, this working, right? Okay. Yeah, thank you very much. Thanks for the organizer for putting together such a nice workshop. So basically, I'll talk about some new progress in the problem of scaling limit. In particular, I'll discuss some new method, and new technologies in proving such scaling limits. So I'll discuss the so-called six-vertex model, which is a two-dimensional statistical mechanics model. The first version of this model introduced by Pauling. It's a model for square ice and planar crystals, etc. Well, okay, so there are many questions one can ask and address for this model. For example, the limiting shape or the counting configurations, entropy questions, fluctuations, Gibbs measure, or Gibbs states, or phase transitions. But in spirit, closely related with the theme of this workshop, I'll talk about the stochastic. So I'll talk about stochastic SPDE scaling limit as a description of large-scale fluctuations in different scaling regimes. So before I even define the model, let me quickly outline the main results. Three results. So first, there's a special class of six-vertex model called stochastic six-vertex. A natural notion of height function can be defined for each configuration. We're going to show that under a so-called weakly asymmetric regime and under so-called parabolic scaling, which means I'm going to scale the x direction by epsilon, scale the y direction by epsilon square. And then the height function fluctuation is going to converge to the solution of KBZ equation under suitable tilting, recentering, and so on. Okay. Second result is another special class of six-vertex model called symmetric six-vertex model. And we're going to look at the so-called Gibbs states. We're going to prove that if we tune a key parameter of the model to a so-called ferroelectric disorder critical point, then the densities in density fluctuation in the Gibbs states, you also do this parabolic scaling. You're going to converge to stationary solution of stochastic Burger's equation. So we can describe Gibbs states in large scales by nonlinear stochastic SPDE. Finally, back to stochastic six-vertex model, the same as the first one. The result is six types of vertex. Well, if we tune weights of certain types of vertex to zero, again, the height function fluctuation converges to, first of all, there was a hydrodynamic limit which says the height function converges to this PDE as hydrodynamic limit. This PDE is this term is like a linear hyperbolic equation. The second order term is like sort of regularization of that. So subtracting the hydrodynamic limit, we show that the height function fluctuation converges to this stochastic PDE, where this noise is a two-dimensional spatial noise. Okay, those two noises are space-time y noise, 1 plus 1 space-time y noise. This noise is two-dimensional spatial noise, and there are some other terms depending on the hydrodynamic limit. So we're going to go through these results one by one, but first let's define the model, right? So okay, it's a very simple model. On the two-dimensional lattice Z2, each vertex, each point carries one of the six types of vertices, and each type of vertex correspond to a number called weight. So the model is defined by 6 parameters. The only rule is that two nearest neighbor vertices should be compatible. And the compatible means if you suppose at a certain point you have a line going up, then the point above this point should have a line going down. For example, the vertex here above this vertex, it can be this one, but it cannot be this one. Okay, so according to this rule, all the little lines get connected and form a global configuration with long and continuous lines. Two lines here can touch at this sort of vertex, but here they only touch and they are not crossing. So the probability of having such a global configuration is simply proportional to the product of weights of all the vertices. So each point you have one of the 6 numbers, you just multiply all these numbers, and there's basically probability that you can find such a configuration. Okay, let's start by the first result. We're going to look at a special class. No, this is a general class. This is a general definition of 6-vertex model depending on the 6 parameters. Well, there are also some other equivalent definitions in terms of, not in terms of lines, but in terms of arrows. We also stick to the line the language of lines. By specializing some of the weights, we have a special class of 6-vertex models. So the first one is called, this one is called the stochastic 6-vertex model, introduced by Guo and Spong in the 90s. Instead of 6 weights, only depends on 2 weights, B1 and B2. So the 6 weights 1, 1, B1, B2, 1 minus B1. What's special for this choice? It's special because suppose here you have a vertex of this type, have line going up, and suppose here you have no lines going in here. The question is, what is the compatible vertex here? The only compatible one is either this vertex or this vertex. Now this vertex carries a weight of 1 minus B1, and this carries a weight of B1. So this means once you know this vertex and this vertex, you can sample a Bernoulli variable with probably B1, you choose this vertex, probably 1 minus B1, choose this vertex. This is very interesting because now once you know all the vertex on this diagonal, you can randomly update all the vertices on this diagonal. You can keep updating in a Markov way. In other words, suppose you look at this model on the first quadrant. Once you know all the vertices on the boundary of the first quadrant, you can just fill in the configuration in a Markov way. So this is why this choice is special. Now, because I want to eventually talk about the KBZ equation limit, which is 1 plus 1, so I'm going to think about the vertical direction as time. Okay, so there's a natural notion of height function defined for each configuration, which is called n. The height function takes integer value. So here you can see the picture. It's 1 here, 0 here, negative 1. Basically, crossing a line, it changes by 1. So this is the height function defined on the 2-dimensional plane. Now, if I fix the time horizon, you are going to see a 1-dimensional height profile. If I change this time horizon, the 1-dimensional height profile is changing. Okay, so now you see somehow you have a changing height profile. It's already a little bit similar with the situation KBZ equation. A nice way of thinking about this model is, take this upper plane, fit into the system a bunch of lines, and let them evolve. in a Markov way. If you like particle systems, you can also think of this as a one-dimensional particle system where the lines just trace out, where all the particles are always jump to the right, and all these lines trace out the trajectories of the particles in the space-time. But I'm not going to talk about particles. I always stick to the line language. Okay, so for this model, if B1, B2 are equal, then this model is symmetric about this diagonal because all the weights are invariant and they're flipping about this diagonal. This means when B1, B2 are equal, you can follow the change of height functions along this diagonal. But if you do this, right, you look at the height function along this diagonal, overall the height function not going to grow or decrease because it's symmetric. So we're going to look at the case that B1, B2 are different. And if B1, B2 are different, then there will be a characteristic direction, which is not necessarily the diagonal direction, not necessarily 45 degrees, but there's a direction along which the height function could, along which you could possibly observe some growth of height function. Okay, in a suitable sense. Let me explain what this means. Okay, so here's the result. We're going to look at a so-called weakly asymmetric regime where B1, B2 are different, but the ratio very small, very close to 1. And besides taking this choice of B1, B2 parameters, I also fix a rho, which is the density of lines, so how many lines you fit into this system. So with these 3 parameters, basically we show that the height function n under suitable tilting, recentering, etc., converge to an equation of KBZ equation. So let me explain what exactly the left-hand side means. So here I'm looking at the height function at a large time scale epsilon inverse 2 and large space space scale epsilon minus 1 is parabolic scaling. But here mu is a characteristic direction. So in other words, I'm going to look at a kind of a parallelogram region which is parallel with the characteristic direction. And then I map this parallelogram to a rectangle, right? And look at the fluctuation of the height function in the rectangle. Okay, so here we also have a minus rho x. What this does is you see this height function is kind of tilted because the height function is always bigger on the right and smaller on the left. And in particular, the more lines you have, the more seriously the height function is tilted. So by subtracting this rho times x, we just make the height function flat, right? Then you can discuss the fluctuation around the flat height function. And finally, there is subtracting this mean velocity is proportional to t, and these are just the recentering of the height function. Okay, so for SPDE community, the combination of 2 terms here are just the famous 1 over epsilon renormalization constant. Okay, so under recentering tilting, we prove this KBZ limit. Moreover, the drift constant here, lambda, as well as the characteristic function, this slope, this mu, have a explicit formula in terms of the parameters we fix B1, B, in terms of the parameters we take the B1, B2 rho. And also, the coefficients in the KBZ equation also have explicit formula in terms of B1, B2 rho, but in the limit B1, B2 are the same, so yeah, B1. So I'll spend maybe 3 slides or so to explain the proof. Roughly speaking, the proof is based on the Kohlhoff transformation. It's based on this fact, which is if H satisfies the KBZ equation, then exponential H satisfies the Heat equation. So this sort of strategy or proof were first used by Bertini Giacomi when they study the weakly asymmetric exclusion process. So the key step in order to carry out this argument is to find at microscopy level, find a discrete heat equation to start with, discrete stochastic heat equation. So here is our result. So here we do have a discrete stochastic heat equation, kind of heat equation on the microscope level. So first, we have this sort of exponential height function at the microscopy level, well, with all the recentering and tilting. It doesn't have to be E. So here the tau is B2 over B1, but it's exponential height function. The proposition says that there exists a random walk with transition probability, transition operator P, such that this exponential height function satisfies this equation where M is a martingale. This is our discrete equation. Okay, why can we find such a discrete equation? Let's give a sketch a proof. It's based on duality, as Ivan mentioned in his talk. So, okay, so let's define something called ny, but this is basically the height function. It's very close to height function. But okay, so basically, for each fixed t, each fixed time horizon, we have the coordinates of the lines. So here, this is the coordinate of the first line, this is the coordinate of the second line, etc. We also have the negative first line, negative second line, etc. So we have all these coordinates. Now the ny, well, y is a kind of sample point, which is somewhere here, for instance. Right, take this y, ask yourself what's the maximal line index such that the nth coordinate of nth line is less than y. Okay, basically this counts how many lines to the left of y, essentially. And the height, well, since height function changes by 1 when we cross the line, height function is roughly this object, but up to some normalization. Okay? So for the rest of what I said, you just think of this as height function. It's fine. Okay, so here's the crucial thing in order to get this equation. Now here I take a sample point y, test point y. Right? So now I'm going to take k test points, y1 to yk. Look at this exponential height function at each yi and take the product of them. Now, condition on, so suppose you already know the configuration below this time, which is this filtration. Right? So condition on this filtration, you evolve the 6 vertex lines by time 1. Okay? And then take the expectation. This is what the left-hand side is saying. Now, what the right-hand side is saying is, okay, so here, these are just k numbers. But now I take another different, take a different point of view. I think of these as the coordinates of another 6-vertex model with k lines. Okay, so I have 2 6-vertex model. This one and another one which is not in picture with k lines. So for the right-hand side, I'm going to also take this product of exponential height function. But sum over, okay, so this P6VK is a probability transition for the other 6-vertex model with k lines. And now I let the dual system, which is the system with k lines, to evolve for time 1. Okay, so I sum over all the possible next step coordinates, which is called y prime, and this is nothing but expectation. So this is just this relation just says you have 2 dual systems, both are 6 vertex, and if you there exists the so-called duality function. In this case, is product exponential height function, such that if you evolve this system by time 1 or evolve the other system by time 1, under the expectation they're the same, and this is called duality. self-duality, because the dual system also six vertex. Okay, so why this is important? Because if you take the k equal to 1 in particular, then you get something like expectation of exponential height function with this product, without the product, is equal to one line six vertex transition probability times the exponential of height function. That's exactly essentially that's the two terms here. Okay, so since this is true under expectation, without expectation you can expect this is true with the martingale here. Yes?
What is the p, small p here?
The p is there exists a random walk with a transition probability p, a transition operator p, and the p is roughly speaking is just this transition probability for six vertex with one lines. The slides are different because here I also have this all the tilting and the recentering and so on. So this z is not really exponential height function with other terms. But roughly speaking, this p is just the transition probability for one line, one body system. Okay, of course the proof doesn't go this way, but for the proof you also need to really look at the definition model and look at what's really this martingale. But that's basically how it works. Okay, so what can we do with this discrete stochastic heat equation? Right? So we have this equation, this martingale. Basically, we want to show under the parabolic scaling, convert to stochastic heat equation. While the random walk here, P, converts to a Brownian motion, this is kind of standard. What's non-trivial is to show that this martingale converts to space-time y noise times the z. And for this, we need to show the quadratic variation of this martingale converge to a quadratic variation of c z. Well, c is space-time y noise, so the quadratic variation is z squared. It remains to show the quadratic variation converge to z squared. We also need to prove tightness, etc. And actually, for this model, somehow the Burkholder inequality doesn't directly apply. We need to bound the moments by hand, etc. But then I'm not going to talk about it. So, okay. So the problem here is if you actually write down the quadratic variation of this martingale according to the definition model, the quadratic variation looks very far from z squared. So, well, the precise expression here doesn't matter, but basically the quadratic variation looks like product the two functions, and each function is involves z and this p acting on z. So p is a random walk. Okay, so this is always the difficulty in proof such result. Okay, quadratic variation looks very different from z squared. But here is a key proposition. It says this product here, or this quadratic variation, you can subtract z squared. This is what you want. This is z squared, and then you get a remainder r. Presumably, you want to show r is going to 0. But if r just simply goes to 0, then you have this z squared multiplied by whatever constant here, then there's other constant here, and combine all these constants, you get this constant in the limit. But the problem is this remainder does not vanish pointwisely. So this remainder, if you really write down everything carefully, this remainder is a kind of complicated linear combination of quadratic terms like this. They involve the derivatives of the exponential height function. And they are actually huge. By dimension counting, they do not vanish. Okay. So the key proposition saying, okay, so pointwisely this remainder doesn't vanish, but under average, so when you integrate over time, a certain norm is actually very small. So this is the significance of this key proposition. So it says these huge chunks actually small when you integrate over time. This is called self-average. So how do we prove such a self-average? Well, this is the key point of the proof, right? So, so basically, if you go back to the Bertin-Giacomin case for for asymmetric exclusion process, there's a kind of a magic identity, right, for the heat kernel, but this is not available in our case. And then because the time is discrete and so on and so forth, there's no such hydrogen limit machinery we can use. How do we prove this? So proof depends on self-duality. So, okay. So let's first look at the first line here. Okay, maybe let's just summarize what I said. It says that so far as we can find a discrete stochastic heat equation, we want to converge to limiting stochastic heat equation. Right? So for this, we only need to identify the martingale term as a right quadratic variation, but we have error terms, and we want to show self-average of error terms, which means error terms smear out when you average over time. Okay. So for this, we prove, to prove this, we use a self-duality. So before I used the duality result where the dual system has only one line in order to derive the stochastic heat equation, the discrete stochastic heat equation. But now I take the duality with dual system being two lines. Okay, so you have a product of two exponential height functions. Do some sort of expectation, and duality says is equal to the transition probability kernel for two body six-vertex acting on the product two exponential height function. Okay, so you see all the question is how to bound quadratic terms like this, and duality gave you some identities for the quadratic terms. And I didn't tell you earlier that actually, well, this exponential height function is a duality function, but actually one has another duality function, which is occupation variable times the exponential height function. This occupation variable is just defined like the indicator function where there is a line at this point. That's it. Okay, so we have a second duality in some sense for this duality function eta z. So why is this important? Why is this related with bounding these terms, right? So here somehow you can make use the fact that height function is integer valued and also changed by 1. And just use the details of the model to rewrite these terms you want to bound as some sort of linear combinations of quadratic forms of z and eta z. Okay, and then the key point is to show that these guys, that this kind of quadratic forms of z or eta z's have time decay. If you can get some time decay, then average over time, you can show it's small. But in order to show these guys have decay in time, you can turn to the right-hand side. It boils down to show some sort of decay for this two-point transition kernel. Okay, so everything boils down to proving certain decay of this two-body six-vertex transition kernel. So the key point of duality method is, this many-body system. The question turned to only one-body and two-body system. And somehow you also need to bound the gradient. Okay. So this is just a two-body six-vertex model. In principle, you can just write down these kernels. It's not hard to solve them. And to prove some decay, usually you go to the Fourier space. Here you can also go to spectral space and some beta ansatz and write the kernels in terms of complex contour integrals. And then via 20 pages of steep descent, we can prove such decay. And that's basically the story. Okay, so the conclusion is, height function fluctuating converge to kbz. Now, we can also, as a remark, we can also prove we can also prove KBZ equation limit in a rarefaction fan. This means now in your system you have all the lines coming from the right, but on the left hand side there's no line. And then there's a rarefaction fan forms here, where here density is 1, here density is 0, and here is between 0 and 1, right? And we can prove if you fix any direction inside the rarefaction fan. This means you fix any density between 0 and 1. Along this direction, we can have a KPZ equation limit. Okay, so the coefficient of the KPZ equation limit depends on which direction you fix. Okay, so this is the first result. Turning to the second one, we're now going to look at another special class of six-vertex model called symmetric six-vertex. Okay, so while the stochastic six-vertex model depends on 2 parameters, B1, B2, now symmetric six-vertex depends on 3 parameters. So the 6 weights are AA, B, B, C, C. This symmetric six-vertex model has a much longer history than stochastic six-vertex. It dates back to 1930s. And there are many questions about this six-vertex model. So let me, well, it's a model which has a very rich structure and behaviors. Let me just briefly describe the physical prediction on the phase diagrams or behaviors of this model. So there's a physical parameter, the key parameter here called delta, defined in terms of A, B, B, C, C. And depending on the value of this parameter, the behavior of this model, there are 3 phases of this model. So this you can think of this like the temperature and EC model or something. So when this parameter larger than 1 is called a ferroelectric phase. When between 1 and -1 is disorder, smaller than -1 anti-ferroelectric. We're only going to look at the ferroelectric regime where delta larger than 1. But we are going to tune this parameter delta down to 1, which is the ferroelectric disorder critical point. And at the same time we tune the parameter down to 1, we are going to rescale the system parabolically. And then we are going to prove that the density, line densities in the Gibbs states you obtained converge to stationary solution of stochastic burgers. Okay. So this is another instance of deriving a nonlinear singular SPDE near a critical point. When you tune into the critical point and also at the same time rescaling, you get a nonlinear SPDE. This close to the spirit of the work of Hendrik and Jean-Christophe Murat for EC model. So I said Gibbs states, right? What are Gibbs states? Gibbs states are infinite volume translating invariant ergodic measures for this model. And these are the crucial objects in order to understanding such kind of statistical mechanism models. Like EC models can also talk about this. And Gibbs states usually obtained by imposing certain boundary condition and send volume to infinity, or by imposing certain kind of external fields. Here we're going to take horizontal and vertical external fields, H and V. And by taking different horizontal, vertical external fields, actually we're going to get different Gibbs states, different infinite volume measures. And these different Gibbs states differ in the sense that they have different horizontal or horizontal or vertical line densities. So in other words, what I said is there should be a mapping from different values of external fields to different Gibbs states with different horizontal or vertical line densities. And here the conjectural picture for this mapping. So here, this is a graph for different values of horizontal, vertical, external fields. Right picture, each point here is like a Gibbs state. Okay, so here, little h, little v are horizontal, vertical line densities for each Gibbs state. Okay, let me explain the picture, this conjectural picture. So when the horizontal or vertical external fields are very positive or very negative, forgot to say what these external fields do, right? So basically they reward the occurrence of horizontal lines or vertical lines. For example, here you have exponential, instead of the weight b, you have exponential h. So when h is very positive, the configuration favors the horizontal line. Okay, so they just encourage encourage the horizontal and vertical lines. Therefore, when the horizontal or vertical external fields are very positive or very negative, basically the configuration has only horizontal lines or only vertical lines or no lines. And these are called frozen phases. And there are the white regions here, A1, A2, B1, B2. They're mapped to Gibbs states with trivial line densities like 1, 0, 0, 0, 0, 1, etc. Okay, mapped to the four corners. So what's interesting is the dark region here, D1, D2. These two regions are mapped to these two dark regions. And Gibbs states in these two dark regions are called disordered Gibbs states. Their behavior presumably should be conformal field theory, but not much is known except for the dimer or free-forming case. So we'll be interested in this so-called conical points. There are two conical points terminating the two dark regions. Okay, there are 2 points here. Each of these conical point is mapped to the whole curve, which is the boundary of this length region. And okay, which point on the curve is mapped to depends on which angle you're approaching this conical point from dark region. Okay. And this is a one parameter family of Gibbs states, and they're usually called stochastic Gibbs states. Basically, we're going to show for this one parameter stochastic Gibbs states that this is a sample of a certain stochastic Gibbs states. Basically, if you this is infinite volume, configuration. If you follow a characteristic direction, and then rescale parabolically, you can derive the line density fluctuation converge to the stationary solution of Skarsberger's equation on the entire plane. Okay, so here the result, the precise statement. Well, basically there is a convenient choice of the parameters called Baxter parameterization, but it doesn't matter. So basically you can choose a ABC in such a way that, and then you choose a HV on this curve, okay? So for the remainder talking, I forgot about the external fields. What matters is the line densities here. So choose 3 parameters and choose a line density HV on this curve. There exists a Gibbs state. That's the first statement, but that's not proved by us, but I'll explain in the next slides. And now we look at these Gibbs states. We can tune these 3 parameters ABC in such a way that this key parameter delta is tuned down to 1, to the critical point. And then look at the vertical line density around this number V. This fluctuation, again, you rescale parabolically and follow the characteristic direction, convert the stationary solution to Skarsberger's. Well, you can also, for sure, you can also look at the horizontal line density, the fluctuation, or you just do the parabolic scaling in the other way, also get a Skarsberger's equation. Okay, and moreover, the characteristic direction as well the coefficients in the Berger's equation have explicit formula in terms of the line densities, and here you have another freedom you can take, which is the C here. So how do we obtain this result? So we can prove this theorem thanks to a very nice connection between stochastic six-vertex and the symmetric six-vertex. So here's the connection between the two models. Okay. Again, stochastic six-vertex depend on 2 parameters. Symmetric six-vertex depend on 3 parameters. This connection says, suppose you're given a symmetric six-vertex model with 3-parameter ABC, and therefore you have this delta defined via ABC. Then, okay, then define the B1, B2 via ABC in this way. Okay, and look at the stochastic six-vertex model on the first quadrant with parameter B1, B2. So given symmetric six-vertex, we look at a stochastic six-vertex. And also, we fix the line density V and H. So here, this is the first quadrant stochastic six-vertex model, right, with B1, B2. Now I'm going to fix the density of line inputs. So this is called V, and the density of the lines we input in this way. So this is H. There are many lines here. And this gives you a stochastic six-vertex model on the first quadrant. And H and V are such that they're on the boundary of the length regime. Okay. Okay, so this equation just says you are on the boundary of the length area in the phase diagram. So Aguirre will prove that this stochastic vertex model is stationary. This is very important because you know it's stationary, then you can send the origin to negative infinity, and therefore get a Gibbs states. Okay, so this is how Aguirre, which is a student at Harvard, construct the Gibbs states for. Okay, so it turns out that this Gibbs states on the entire plane is a Gibbs state for the symmetric six-vertex model with a given ABC here. Okay. So this is a nice connection between the two models, and thanks to this connection, we can get result. We can obtain result for the symmetric six-vertex because, well, what is the line density, right? So height function changed by 1 when cross the line. So essentially, line density kind of derivative height function, and stochastic Burgers is kind of derivative of KBZ. Okay, that's how it works basically, up to some other technical subtleties. Okay, if there's no question, okay. So having derived stochastic PDE in the parabolic scaling, one might wonder what happens if you rescale the x direction, y direction in the same way by epsilon. So we turn back to the stochastic six-vertex model and prove that if you do this hyperbolic scaling, get the stochastic so-called telegraph equation. Again, depends on 2 parameters, B1, B2. Okay, so again, how can we derive some equation, right? You need some microscopic relation. For KBZ, we have the relation because of duality. Now we have so-called 4-point relation. This is observed by Ivan Corwin, which means if you look at the exponential height function, again called z, at 4 neighboring points, right? 4 neighboring points like this. The exponential height function at 4 points satisfies such a relation where this is some random variable you can characterize very explicitly. For example, you have the conditional variance or something for this noise. So if you, well, this you see here, this is almost discrete derivative. So you can play around this equation, rewrite this as the following form, where these are the discrete derivatives. So this means if you, okay, so discrete derivative divided by epsilon is continuous derivative, right? So this means, well, you have second derivative here. You need to, well, if you want all the terms survive when you take limit, you need to tune the parameter such that B1 is close to 1 because there is one more derivative here, right? The B2 close to 1. And this means in your configuration, so 1 minus B1, 1 minus B2 going to be very small. So your configuration, you can only see long vertical or horizontal lines which occasionally turn. Okay, so that's the regime we derive our stochastic telegraph equation. Okay, now, okay, they observe this relation, which is this, and they show that if you tune the parameters that was said, the rescaled, hyperbolic rescaled exponential height function converge to this hydrodynamic limit or law large number. This is called the deterministic telegraph equation. And they conjecture that if you subtract this hydrodynamic limit, it should converge to some sort of random telegraph equation. And we prove this. So our result is if you subtract the hydrodynamic limit and amplify the fluctuation, then this is central limit scaling, it converts to this linear stochastic SPDE stochastic telegraph equation where the right-hand side, can see here is a two-dimensional spatial noise with boundary condition. If you look at zero boundary condition, if you look at the first quadrant, this coefficient depends on the hydrodynamic limit. Okay, you can also translate this in terms of height function. This z is exponential height function. You can also get a limit for height function, but this is not very illustrating. So, so let's just look at the exponential height function. Okay, so to prove that our fluctuation converge to solution to this stochastic telegraph equation, we should first understand what is solution to the stochastic telegraph, right? So this is a linear equation, and you can find a kernel which is called Riemann kernel, such that the solution to this equation can be written as an integral of this Riemann kernel acting on this right-hand side. It's like for heat equation you have a heat kernel. So here you have Riemann kernel. Now the key to prove is this result is, okay, we first find a discrete analog of this integral form of solution. So write the u here as a summation instead of integral, and the discrete Riemann kernel some noise. And here the variance of this discrete noise depends on z and gradient z. Again, you see this kind of phenomena as in the KBZ case, where you look at your quadratic variation noise, but the quadratic variation noise depends on the solution. So this is general phenomena, right? The general difficulty. Now we want to use the Martingale central limit theorem. We want to show quadratic variation of u convert to quadratic variation of this guy convert to the kind of variance of this guy. The difficulty in showing this is u depends on this discrete noise. Discrete noise depends on the z or gradient z. Limiting solution depends on this d, and d depends on the hydrodynamic limit phi and the derivative hydrodynamic limit gradient phi. This hydrodynamic limit is only Lipschitz continuous, not differentiable. So maybe you want to show, if you would have a z convert to this guy and a gradient z convert to gradient for the limit, whether you're done. But it's not true. The derivative doesn't convert to derivative of the hydro limit. Okay, so the strategy is in few words, just write the z again as integrals or sums involving discrete Riemann kernels, and then do some iterations, and essentially we cross the bridge by again using the averaging effect and also regularity of the Riemann kernel. Okay, so basically we have have some future directions on this. Actually, we observe some relation between the 4-point relation and the duality relation. They're essentially the same relation, right? So essentially, starting from the same microscopy mechanism, you do this scaling at this equation, that scaling at the other limit, but somehow maybe you get something between. And also the duality method also works for very general models. Some grad student working on showing KBZ limit for a higher spin version of the 6-vertex model. Okay, thank you for your attention.
Thank you very much. Are there any questions? Yes?
So in the 6-vertex model, if you take your transfer matrix along the diagonal direction, I mean, you took it along one of the lattice axes, but just take it along the diagonal direction. And then if you make the lattice spacing in the diagonal direction very small, and you will converge to the XXC model.
Oh.
So my question is, I mean, can you prove similar type of results for the XXC model?
I never thought about that.
Okay,
yeah, I can discuss later. Yeah. It sounds interesting.
Any other questions?
Yes?
Is there any possible dependence on the domain? So you've chosen a square domain. Have you thought of solving it on a parallelogram?
Yeah, in principle, I think this is more like a technical question. In principle, it should also work. But then, okay. Yeah, I assume if you take some general domain with some sort of way to define input lines, right, on the boundary, then you can update what's going on in the bulk. I assume you can also prove such result for height function.
Any other questions? All right. Well, thank you again.